Hi everyone, and welcome to Module 0.6, Statistical Reasoning in Everyday Life. Here's your vocab, pause if you need to. So let's first talk about why do we need statistics. So we're not going to be doing anything that requires a calculator, but you will have to do some basic calculations. But the key thing that we're going to be doing is understanding how to accurately interpret statistics. So it is easy to misinterpret the information because we don't understand the terminology or what the data really represents and who is in the data. Like there are always those, remember, curious, skeptical, right? So there's always things to investigate. There's a lot of misinformation out there. So one way that we interpret data is we describe it, we measure it, we organize it into something meaningful. This can also be misleading, especially depending how it's presented to us. Here's an example of how marketers might want to market their product. If their product is supposed to, let's say it's a hair growth company, right? And it's like, look at our product here in this orange color. And look how much better than we are than the competitor who's way down here. Well, if you look at that y-axis and you see it's not starting at 0, right? This one is a not truncated. See the difference there? Oh, competitor A versus our company, not much of a difference. It doesn't look flashy. Doesn't look like people are going to click and buy. This makes people buy. So there are ways to present and organize data to make it appear a certain way. And just for reference, histogram, that's your vocab, bar graph, and polygon is the line here showing the data points. Okay, so a measure of central tendency is any measure that is trying to find the center of the data. So there's mean, median, and mode. So mean, you add up all the data points, divide by the number of data points that there is. You can do that over here and see that the mean is 5. Median, you're finding the middle. So in this example here, you'd start with the 8, you'd start with the 1, you'd go to the 3, 7, 4, 6, etc. until you find the center. Mode is the number, the data point that comes up most frequently. So mean, average, median, find the middle. Think of the median on the road. The median of the road is that center curve of the road. And the mode, M-O mode, M-O most. And then the last thing that you can use for reference is the percentile rank. So if the percentile rank, if you are in the 50th percentile for your height, let's say, then you are right in the middle. You are average height for your age, let's say. So 79th percentile in math in a competition means that you are higher than 79% of competitors. So sometimes these things can be skewed. And what is most commonly skewed is the mean. So there's positive skew and there's negative skew. And you need to know the difference and what they look like as well. So in a positive skew, the mean is higher than the median. So median's back here, mean is up here in a positive skew. Mean is higher. In a negative skew, the mean is actually lower than the median. So the mean is the one that gets skewed the quickest. If there's one data point, for example, Elon Musk walking into Starbucks, what's the average income? Well, that's going to change dramatically when Elon Musk randomly walks into your local Starbucks, right? So everyone now is a billionaire. So median, when you're trying to find the middle, you start with the highest and the lowest, and you move each data point to find the middle. That's not really going to be thrown off by Elon Musk walking in that restaurant. So that's going to be a lot more meaningful, more reliable. So always take note if there's some sort of skewing of the data. If the data is in a normal distribution, that means that the mean, median, and mode are all the same. That's good. We like that. We like that kind of data. Okay, so not finding the center, measure of central tendency, but finding how does the data differ? How much does it differ? Because if we collected a bunch of data about people walking into that Starbucks, but the data is all over the place. Is that going to tell us something meaningful about the average income in that area? Or what does it tell us? So the range. So range is the one you probably already know, measure of variation, where you take the highest number and you subtract the lowest number. So you would take the highest income, the Elon Musk income, and you would subtract it by the lowest income, and that's your range. You probably get this huge number. You would get this huge number. And what does that tell us? It's easily skewed by those extremes, so it's not always useful. Standard deviation is much more reliable. And what standard deviation means is how much does each data point vary from the mean score? And so if the standard deviation is high, that means a lot of your data isn't close to the mean. And remember, ideally we like this normal distribution. So that means your mean is definitely skewed because your median and mode are not near your mean, right? It could be negatively skewed or positively skewed. So in a normal, let's say, so we want, just to be clear, so we want a low standard deviation because that means our data is all close to here. Now, this is another thing you have to know about. Again, you don't have to calculate standard deviation. You do have to be able to calculate range. But for standard deviation, you need to know on a normal curve, not on one of these skewed curves. You're not going to have to know that. But on a normal curve, how many data points scored within one standard deviation? So if you look on this graph, you see these dotted lines. Each one of these represents a line of standard deviation. This one says -3 standard deviation, -2, -1. M is for the mean, so here's our mean, and we also know it's our median and our mode because it's normal. Here's our +1 standard deviation, 2, and 3. Okay, so within one standard deviation goes both directions, from this dotted line all the way to this dotted line. What percentage of our data in a normal distribution is within one standard deviation? It's always the same answer. So it's a number you have to learn and remember. It's called the 68, 95, 99 rule. So 68% of the data falls within one standard deviation of the mean. If it is within 2 standard deviations, it is 95%. And if it is 3 standard deviations, it is 99.7%. That's all of our data points, right? If we include, and obviously that's not as many, right? It's 2.35% of the data is going to fall here. Just imagine little dots here representing each data point. So if we said that the mean is 70, so imagine 70 is right here in the mean, and we said the standard deviation is 5, what percentage of people scored between a 70 and a, so here's the mean, 70, and a 75? Well, we said the standard deviation is 5. So that means this is 70, this is 75, this is 80. See how I'm counting by 5s? And this is 85. Going the other way, we said our mean is 70, so this is 65, this is 60, and this is 55. So how many people scored between a 70 and a 75 would always be 34%, okay? Because it's within one, it's actually a half of, right? If it is, how many people scored between a 65 and a 75, and the standard deviation is 5, they will always give you the standard deviation. You do not need to calculate it. The answer would be 68%. Okay, and we'll practice that more in class. So we can describe statistics using those other numbers, how much they vary, what does the center of the data look like. But in inferential statistics, we're looking at, does this data help us draw any useful conclusions? And is it meaningful? So looking at a sample, that means who is in the study. We want 3 important factors. We want a sample that is representative. That means that if you are studying a population, let's say you are studying all seniors in high school in the United States, you can't actually study you can't put in your study every single senior in high school. And so what you do is you get a representative sample. If you choose only seniors who go to your school, is that going to be representative of the entire country? No, right? Many old psychological studies were only conducted on white middle-class men. So some of those studies have been retested and found to not make sense for certain groups. Sometimes they do make sense for everyone too, but because they weren't representative, that's not good data to draw conclusions on. We want representative so that we can generalize about the whole entire population. And if it's not generalizable, it's really not telling us anything beyond what's true of your high school and seniors in your high school. Okay, the next thing we want is a large sample size. If you see that a study was conducted on 10 high school seniors in your school, that's not really useful. What 10 kids thought, maybe they're all in like certain level of classes, certain sports, and they have a different perspective than everyone else. So large sample sizes, big numbers in a study is better. And then if the study has been done one time, people have tested this hypothesis, this theory, one time, that's not as useful to us as meta-analysis. Meta-analysis is when we have a whole bunch of studies and we interpret the data of a bunch of studies. Okay, so when researchers look at their starting point, they have a theory and they've drawn a hypothesis. They actually start their research with the null hypothesis. This is a scientific way of approaching things. So I wonder if music impacts studying and improves test scores. Well, you start with the null, which means I'm going to start my experiment from the premise that this one group is going to listen to music while they study and the other isn't. And the null hypothesis is the idea that it's not going to make any difference. There will be no difference between our experimental group and our control group. That is our null hypothesis. And you work to see if you can prove that to be true. Can I prove the null hypothesis to be true? And if I can't, if the information is statistically significant, that means that there is a difference between my group that listened to music and my group that didn't. And statistically significant is actually a numerical data meaning. It's not just like, ooh, significant, very important. No, it means that the p-value, and you don't need to be able to calculate it, is less than 0.05. Okay, that means, so 0.049 and lower, p-value means that the data is statistically significant. That music listening group, that music likely did have an impact. You can't say that it definitely did because there's a 0.049 or less. There's some small chance that there's some other reason that group did better. And that's assuming that we already have a representative sample and a large sample size, right? It's assuming we have good otherwise data, but there's a 0.03 chance that it's because of some other variable. But there's a really strong indication here. So what it does say, statistically significant means there's a really strong indication that listening to music impacts your test scores. There is effect size. So effect size is looking at the strength of the relationship between the two variables. So in our previous experiment, it was listening to music, improving test scores. So it is your test scores in the music. So is there a difference in those that listened to music and those that didn't? So let's say that it was statistically significant, right? That might not make much practical significance. So let's move on to a different example here. So your textbook talks about this example where there was a large study about IQ scores, and they were trying to see if the oldest sibling was had a higher IQ score than younger siblings. And the data proved to be 0.049 or less, so it's statistically significant. And I think it was like 200,000. Was it 200,000 or 20,000? 20,000 people. 200,000 would be a lot. 20,000 people, which is still a lot of people. But the difference was 1.5 IQ points. So the vast majority is not determined by birth order, and there's some other factors at play here. So effect size is comparing those groups and tells us, like, if there is a large effect size, that means that the independent variable might have had an impact. So it kind of tells us, like, okay, it's statistically significant, but in real life, does this make sense? Is it practically significant? And then the next thing is confidence intervals. So confidence intervals are comparing, so now we're talking about meta-analysis here. And we have all these different studies. Imagine these different lines being different studies. And these dots are the data points that are the mean for each of the studies conducted. And remember our standard deviation, 68, 95, 99, right? So 95% is within 2 standard deviations. So a lot of times studies talk about a 95% confidence interval. So they're looking at multiple studies and they're trying to find what is the range of variability within the means. So see how this says true mean? So you can't compare within one study. So for example, you want to estimate the average amount of sleep everyone at your school gets per night. You take a sample student, find 95% confidence interval. Is this the true amount of sleep? Between 7.5 and 8.5. So you do not say there is a 95% chance that the true mean is between 7.5 and 8.5. It is if we repeatedly found a confidence interval from samples of this population, 95% of those studies would contain the true mean. So if you look at these people here so here's our population, and we got our representative samples. Here's one study. Each dude here under sample is a different study, okay? And we are trying to find the true mean, and this is saying that we have a 95% confidence that the true mean is somewhere in this range based on all these studies. Okay, so your takeaways, mean, median, and mode are measures finding the center. Which one is the most easily skewed? You do need to know that because they do that a lot, is mean, right? Elon Musk walks into the Starbucks, everyone's a billionaire if we're looking at the mean. Range and standard deviation, easiest one skewed is the range, so we look at standard deviation. We have to remember the 68, 95, 99 rule. Samples should be large, representative, and meta-analysis is best, multiple studies. Effect, we're looking, does the independent variable actually make a difference in a practically significant way? And confidence intervals is looking at the differences between multiple studies. All right, so that sums up Mod 0.6, and I will see you next time. Thanks.